reaction. Only one step you need to follow in this. Suppose this is your alkyl halide, methyl halide you're going to check. Methyl halide has what? Here would be your plain hydrogen. Here would be your dotted hydrogen, which is behind the plane. Okay. And this is in front of you, shown by the solid wedge line. And this side will be your, on the plane of paper, methyl chloride. Okay. If you treated it with the NaOH, in that, in the NaOH, OH acts as a nucleophile. It approaches from the backside. Why it approaches from the backside? Because chlorine is also negative charge. Your OH minus is also negative charge. Negative repulsion is there. OH will be approaches from the backside. You will get a transition state. In this case, what happened? All the hydrogen would be separated. Okay. Make an angle of 120. Right? All the hydrogen would be on the plane of paper, and bond making and bond breaking step would be takes place simultaneously. Means here would be OH and here would be what? Cl. So OH bond formation and Cl bond breaking, CCl bond breaking would be takes place simultaneously. So we know that carbon has a valency 4, but then this transition state has a valency 5. Hence it is highly unstable. Okay. And this highly unstable state, we are not able to isolate by any means, right? And at last, you will get the product in a way. Here would be your hydrogen. The another hydrogen would be below the plane. This hydrogen would be above the plane. And this is OH attached to your substrate. And Cl is act as a living group. Cl minus would go, and it is nothing but living group. Okay, and this living group will be go and connect with this Na. So it may form NaCl. Clear? Okay.
Yeah, ma'am.
Yeah, so this is quite a revision type of thing, which already I have explained. But then here, if primary alkyl halide, your transition state would be more stable, right? Because here would be all hydrogen would present, only 3 atoms are present into the transition state. Because in transition state already your incoming nucleophile is there, outgoing living group is there. Then apart from that, these 3 hydrogens are there. And as the alkyl group increases, in this case, suppose instead of a hydrogen, if there is one CH3 group, what happened? Your 3 hydrogen and 1 carbon is increased from that of the previous structure. And there would be steric hindrance appear in the transition state. It become more bulky. It will become what? More bulky. And hence, what happened? Rate of reaction decreases. Similar thing is happened if instead of here it is also CH3, here it is also CH3. Understanding? So you can see carbon has a size 12 times of greater as compared to hydrogen. And the number of hydrogen are also increases in the transition state. And hence, tertiary alkyl halides react very slow in case of your SN2 mechanism or SN2 reaction. Clear? Fine. Any problem?
Yes,
any doubt about it? If it is, so let me know.
No, ma'am, I got it.
Apart from that, we have learned about the configuration, right?
Yeah, ma'am.
Yeah. So in that configuration is completely inverted. Why it's inverted? Suppose this would be your R rectus, then you will get the product with S configuration, right? Means reactant and the product are mirror images of each other. Understanding? Only your living group and the nucleophile and living group.
Yeah, the product is an inverted image of reactant.
Inverted image of your substrate or the reactant, right? This is due to inversion of configuration. Why inversion of configuration occur in the SN2 mechanism? Due to the negative charge repulsion. Nucleophile and the living group both are negatively charged, right? These two. So it cannot approach from the same side where chlorine would be present. It will attack from the back side, and hence it configuration has been completely inverted, like how umbrella has been turned upside down. Sorry. Yeah, we can say upside down only. When heavy rain is there, that time it would be completely inverted, right? We must have seen. So same thing happen in the molecule as well. Understand? And you said me about this. Chandana has joined or what? Yeah. Chandana.
Yes, ma'am. Good morning.
Good morning. Okay, fine. So I hope this already I have explained you, both of you, and about this, you know, any one of you have don't, not have any sort of problem, isn't it? Yeah,
No, ma'am.
fine. So now we are going to learn about the SN1 mechanism. Fine. So configuration already we have seen inversion and configuration in this case. Shall I erase all the thing or you want to write it?
It's okay, ma'am. I have taken a pic. You can erase it.
Okay. Now what you're going to do, we are going to learn about this SN1 mechanism. Right? What about the SN1 mechanism? What's the long for this? Long form for this, substitution, nucleophilic, unimolecular. Right? This mechanism is two-step mechanism. This mechanism is how long it will be, just two-step mechanism. Earlier SN2 mechanism was one step. This is nothing but two-step. It is unimolecular, means its rate of reaction is depend only on concentration of alkyl halide. Okay. Whenever you have to say concentration, you have to means like embedded it into the square bracket. Fine. Got it? Now, what happened in this reaction? Basically, you have to keep it in your mind, your tertiary halides are more reactive in the SN1 mechanism. Why it is so, that will let you know. Fine. If we see the rate of reaction, tertiary halide is more reactive as compared to secondary, and secondary alkyl halides are more reactive as compared to primary in a SN1 mechanism. Right? Why this happened? Because it has a two-step. In that first step, what happened? Suppose this is your tertiary butyl halide, like carbon attached with CH3 group. It's on the plane of paper. It would be where? Below the plane of paper, and it would be towards you, means above the plane of paper. And if it is connected with your Cl group, Cl, bromine, iodine, any of the alkyl halide you can check. Take in this case. In the first step, what happened? Your chlorine group is completely departed, and you will get the carbocation. Here, carbon, right? This is your carbon-carbon bond, which has an angle 120 in between. They get well separated, and all the CH3 group would be on plane of paper. As your chlorine has been departed with the electron with it, minus Cl minus, okay, what happened? It will generate carbocation, right? And this carbocation is stable, right? How it will be? It is stable. Why it is stable? Because due to electron donating effect of donating inductive effect of each and every CH3 group, right? Yes or no? As a number of resonating group, as number of inductive group would be increases in this transition state or on the carbocation, right? What happens? Stability of your carbocation would be increases. It become more and more stable. Correct. Now, in a second step, this is your step first. In the second step, what happened? This carbocation get attacked by your nucleophile. Right? I'll write it here. In this case, what happens? See, this carbocation CH3, CH3, CH3 with the angle 120 get attacked from the both side, right? So this OH minus can be approaches towards this carbocation from this side, and even it can be approached from the other side, right? Yes or no? And because of that, what happened? Whatever products you will get the two types of product. It will be 50-50% of mixture. correct? So you will get the racemic mixture in this case. What do you mean by racemic mixture? That too, I'll let you know. Wait a minute. So your first product would be CH3 on the plane of paper, CH3 below the plane of paper, CH3 towards U, right? It's been attacked by the OH, right? And another would be OH, and the rest thing would be same as it is. Here it will be CH3. Here it will be what? CH3 with the below CH3 with a dotted line below the plane of paper, and CH3 would be towards U with a solid wedge line. CH3. If you see the configuration for this, what you'll get? All are same, so it's not a chiral, we can't say, but then you can understand about the position of OH. It's completely opposite, and these two products are mirror images of each other, correct? Right? And hence the products we get, that would be the racemic mixture. And this racemic mixture can neutralize each other, and hence configuration, we can't say it is like certain, like R or S. Whatever you will get, that would be the zero chiral. They are completely zero chiral products, because the one's configuration would be cancel another product's configuration. S cancel R cancel yes. And such a mixture is called as the racemic mixture. But then actually, if we see about this reaction, OH minus will not be approached from the front side easily. Why it happens? Why complete 100, sorry, 50% of product, 50% products are not formed? Generally, we must say 50% products are formed, and it will give us a racemic mixture. But then actually, in fact, practically when we perform this reaction, we find it like your inverted product is more. Inverted product is more as compared to your as it is product. Means like configuration of your reactant and configuration of product would be same. That kind of product is less as compared to inverted product. Why this happens? Because when Cl would be depart and form the carbocation, that Cl group, which is a living group, it will be keep here in the close proximity of carbocation. Why this happened? Due to the positive negative attraction between them. Correct? It be in a contact with your carbocation, and hence as it lies nearby the space from where it's leave, from that side OH minus attack would be quite impossible, because Cl has a negative charge and OH also has a negative charge, and hence complete racemic mixture will not be possible. We will get the configuration of a product maximum with the inversion. Okay, understanding? Yes or no? In SN2 also there would be inversion in configuration. In SN1 also there would be the inverted product more. Why this happen? Because the living group will be in a close proximity of your carbocation, and hence OH minus cannot be approached from the same side from the departed living group. Okay, and hence the product from that side would be less as compared to the inverted product. Clear? This is very, very important, because in JEE NEET such kind of questions must be asked with the help
Yes, ma'am.
of like this is a concept, and they may ask you to applicable question on the basis of this concept, right? Clear? And what we have learned? What we have learned, tertiary alkyl halide react more faster as compared to secondary, and secondary will react more faster as compared to primary. Why this is so? Due to stability of your carbocation, either by inductive effect, right, or by resonating effect of the substituent present onto the alkyl halide. Correct? It's not. It won't become a bulky at all, because when carbocation is formed, it will be create a 120-degree angle in between and get separated, well separated, isn't it? So bulkiness doesn't affect the rate of reaction. But then bulkiness may affect the rate of reaction in case of SN. Okay, these basic things you need to keep it in your mind. Clear? Yes?
Yes, ma'am. Yes, ma'am.
Any query, anything in your mind? If it's so, let me know.
No, ma'am.
Fine. Shall I give you one question? Would you like to solve?
Yes,
Yes.
ma'am.
Okay. Let me erase it. The question would be, yeah, in the following pairs of halogen compound, which would undergo the SN2 reaction faster? SN2 reaction faster, they said, and in the substrate I'm going to give you. And you have to tell me the reason as well, why. And another one. Here. Which one would undergo SN1 reaction faster? SN2, sorry.
Ma'am, the first one will go under SN2 reaction faster.
SN2 reaction faster. Why?
Ma'am,
Because
because
when you
there are like more H plus ions, so like the reagent can attack from either ways easily.
depart this Cl, you will get this, right? CH2 with positive charge, correct? Yes or no? This is what? Primary alkyl group or primary alkyl halide, correct? And here if you see, this carbon is attached to 2 carbon and only with 1 hydrogen, correct? So it would
That's
be
secondary.
secondary alkyl halide. What we have learned earlier in the SN2 mechanism, terms already we have learned. Primary is react faster as compared to secondary, and secondary react faster as compared to tertiary. So as it is the primary, it will react faster and it will react slower, right? And vice versa for SN1 mechanism,
SN1.
correct?
Yes, ma'am.
The next one, shall I erase it?
Yes, ma'am.
The other one in this way. And here. Now alkyl group is same, isn't it? The difference is only with living group. Come on, tell me which one undergo SN1 or SN2 reaction faster as compared to SN1? You don't think, SN2 only think, because both are primary alkyl halide, correct? Isn't it? Both are primary. Come on, think over it. You have to. Chandana, Aditi.
Ma'am, the one with iodine will react faster because it is a weaker leaving group, like because of the
Answer
bond
is
length.
correct. Answer is correct. Iodine, yes. The substrate with iodine can react faster.
Because of a larger bond length of iodine with carbon, it can be easily broken, whereas
Actually,
carbon-chlorine bond
iodine
length is
is a
stronger.
large size, right? It is large size atom as compared to chlorine, right? Yes or no? So it acts as a best living group due to size of iodine. It can be depart easily and hence substrate can be react faster as compared to chlorine. Chlorine is smaller in size as compared to iodine, right? So it will take more time to depart. It won't be that fast, means like that easy to leave to compound. Understanding? Due to the small size. Iodine can be easily detached due to the large size. It's a best living group. It can be detached easily and hence can react faster. Okay, substrate can react faster in SN2 mechanism because both are primary alkyl halide. If I break from here, I'll get what? Positive charge. Here also I'll get positive charge, isn't it? So both are primary with a 2 hydrogen on it. Here also hydrogen, here also hydrogen, and here also. Clear? Fine. Shall I give you a few more questions on the basis of these two, which actually asked you in your previous examination? Shall I? Shall I erase it?
Yes, ma'am.
Fine. So the question which is given to you is, which one of the following will be most reactive in SN1 reaction? Think and write down. Which one of the following be most reactive for SN1 reaction? And that first option is given, that is Cl. Second option is given in this manner. Here, third. Here, CS3. And the last one would be now the rate of reaction of SN1 and SN2 is completely depend upon their intermediate state, right? For the SN2, there is a transition state, but then here we are learning for the SN1. For the SN1, it depends on the stability of carbocation, correct? Isn't it? Stability of carbocation is important. So among these 1, 2, 3, 4, whichever substrate will be formed, more stable carbocation.
Ma'am, is it the third one?
Hmm?
Is it the third one?
Third one, are you sure?
No, ma'am, it's the fourth one because there is resonance.
Yeah, very good. Now, if we depart this Cl, you will get the secondary carbocation, here positive charge, right? There is nothing to balance it, isn't it? If you depart this, you will get what? Carbocation in this manner, which can be stabilized by the resonance, right? Your
But it's secondary.
positive charge, it can be like delocalized over here in this 2 carbon, correct? Now, if I remove this, I will get the carbocation in this manner. Whether it is primary, secondary, we need to check it. It will be CS3 with a positive charge, isn't it? It's a tertiary
Yeah.
carbocation, right? But then this positive charge won't be stabilized by anything, correct? But then if I remove this Cl, what happened?
There will be resonance and the positive charge will be stabilized.
Yes. Here will be the positive charge. Here will be the CS3 group. The CS3 group will give an inductive effect over here to the carbocation. Here also inductive effect would be given by the CS3 group. And apart from that, carbon-carbon double bond would be in a resonance with carbocation. So this carbocation would be delocalized within this. So both things would be there. Inductive effect and resonance effect would be present into your fourth compound. And hence your option 4 is the correct answer. Clear?
Yes,
Right?
ma'am.
Yeah.
Yeah, ma'am.
You understood? Both of you understood about it?
Yeah, ma'am, got it.
Fine. Shall I erase? This question asked in your previous examination.
Yeah, yes, ma'am, you can erase it.
Yeah, first one, this one is what? Secondary alkyl halide, right? Secondary carbocation, whatever carbocation will get, that would be the secondary carbocation. This would be allylic plus secondary carbocation, right? Allylic plus secondary carbocation. This would be tertiary carbocation, right? After removing of chlorine, whatever you will get, that would be the tertiary carbocation. And this is allylic plus tertiary carbocation. So as it is allylic plus tertiary carbocation, it is more stable. Fine. Clear?
Okay, ma'am.
Fine. Now write down for the next. Shall I erase it? Write down the next question. The structure of major monohalo product in the following reaction is. The structure of major monohalo product in the following reaction is. Your reaction is in this manner. This is your resonance hybrid, right? This is your CH2OH. This is your OH at the para position plus HCl and heat. You have to write down the products with the answer. First one would be in this manner. CH2Cl. Here it is Cl. Second, again resonance hybrid. Cl, CH2OH. Here it is OH. Third, resonance hybrid of benzene. On it here CH2OH and Cl. And the last, I'm sorry, this will be in this way. CH2 Cl and here it is OH. And the fourth one, that will be completely opposite of third. But you will get here CH2OH and here Cl. What would be the product? What would be the answer? Are you solving? Chandana, Aditi, am I audible?
Yes, ma'am.
Are you solving?
Yeah, ma'am.
This question is asked in a previous examination.
Ma'am, is it the third one?
Ma'am, is it the third one?
Yes. What would be the mechanism for this?
It is SN2.
SN2. Very good. Means primary alkyl halide react faster, right? So first of all, what
Yeah.
you have to just protonize this OH group, right? It will be get protonized with this H. You will get what? OH as it is at its place. Here, CH2, O, H and H with positive charge. As it is positive charge, your chlorine from here, Cl minus, it becomes Cl minus as hydrogen has been taken. It will be attacked here and your OH group will be departed, correct? Isn't it? We'll get the product. Benzene, hybrid with OH, your CH2 and Cl, correct? Yes. In this case, the key you have to keep it in your mind is what? sp3 hybridized carbon show fast nucleophilic substitution. Than sp2 hybridize. Clear? Okay.
Yes, ma'am.
If you protonize this OH, you may feel like that, ma'am, why we have protonized this OH? Why not this? Correct? Because if you protonize this, you will get the carbocation over here. It will be attached to the carbon-carbon double bond of benzene. So it becomes sp2 hybridized. And it is here sp3 hybridized. And because of that, reaction would be processed faster at this carbon instead of this. Understand? Because two OH are there in your substrate. So which OH will be get attacked by the H plus? That needs to be understand. And hence I gave you this hint. sp3 hybridized carbon atom shows fast nucleophilic substitution than sp2 hybridized carbon. Clear? Got
Yes,
it?
ma'am.
Yeah. Yeah, this is quite like unexpected. Let me see whether you're able to go through it or not, but then it's very important. It's a new different kind of mechanism. It's a name reaction, right? It's not given in your text, I guess. Then yes, I'll explain it. Fiborsky reaction is not in your text, right? Isn't it? It's there or not?
Sorry, ma'am. Can you repeat?
Fiborsky reaction.
We haven't learned about that.
Fiborsky rearrangement is not given in your textbook, I guess. As per my knowledge, I haven't seen it in 12th grade.
No, ma'am, it's not there.
Yeah, but then such kind of question would ask you in your JEE, okay, examinations. And regarding that one question I'll give you, like your concepts would be same. That won't be a problem. They won't be, they need to be understand much. But then yes, you should know this. It's very important. Let me ask you a question on the basis of that. Yeah, this one will be write down the major product from the following. I'm not going to write the question you write out directly. I'll give you reaction. Okay. The major product you have to write for the given reaction. And the reaction is in this way. This is your cyclohexane, hexanone, right? As it is ketone, and here it will be bromine. The reaction is given NaOMe, sodium methanoate. Major product you have to write, and your options are first one, double bond OCH3. Then the next second, 5-membered ring. CO2 Me. The next, third one, 5-membered ring with double bond OCH3. And the fourth one, 4-membered ring with CO2 Me. Which one would be the product? Fifth is also given none of the above or more than one of the above. At 12:30 को बैठे time है अभी. Half an hour. Come on, write the answer. Can you solve this? Chandana, Aditi, I'm asking you something, beta. Yes, no.
Yeah,
Can you
ma'am, I'm trying it out.
you're trying? Okay, both of you are trying. Chandana,
Yeah, ma'am.
fine. So what happened in this reaction? Shall I explain or you're able
Ma'am, can
to?
you explain it? Because like we didn't learn about it.
Explain a little bit. Okay, this is your substrate. It's a cyclohexane, right? It has a carbon oxygen double bond, so it becomes cyclohexanone. It's a ketone group, right? And it's your halogen. So now your halogen won't be depart directly. So you can check this is your like ketone group, functional group, and the next carbon to the functional group is a alpha carbon. The other one is a beta carbon, right? In that way, you have to label it. Now, alpha carbon has a 2 hydrogen over here. Among that, I will show here 1 hydrogen, right? Okay. Now, what happened in this case? You have a nucleophile in this OMe, right, with negative charge, because sodium, we know that Na plus, it's a positive, and OMe is a negatively charged. So OMe is your nucleophile in this case. So this OMe will not be attacked directly onto the ketone group, or even not on this carbon directly. What happened? This OMe will be attacked at the alpha position of hydrogen. Why? Because oxygen also have a lone pair and bromine is negatively charged. So this negative ion OMe will not be approached from the bromine side and even not from to the oxygen, isn't it? So it will be attacked onto the alpha hydrogen. Alpha hydrogen will form double bond over here, and the electron of this double bond would be shifted on the head of oxygen. Clear? Understood about it? Yes or no? This OMe would be taken this hydrogen. It took this hydrogen over here. Understanding? This OMe took this hydrogen. So you will get what here? Minus HOMe. Right? This part you need to remove. What would be remain now? Here it will be double bond, right? This is your oxygen with negative charge, and here it will be your bromine. Correct? Understanding what happened or not? This OMe will be taken this hydrogen. This hydrogen and carbon bond has been shifted in between your first carbon and second carbon, and the electron in between carbon and oxygen will be shifted on the head. That become O minus. Now, here, how this group would be depart, that we need to check. Correct? Now, this negative charge would be come back in between carbon and oxygen. This carbon-carbon double bond would be attacked onto the bromine carbon, this another alpha carbon, and bromine would be depart. It acts as a living group now. So when this bromine get depart, what you will get? You will get the ring in this way, right? Right? As this bond is utilized to form a bond in between these two, there is a new bond would be formed, isn't it? And here double bond O, carbon oxygen double bond O. Clear? Yes or no? Up to this you understood or not?
Yeah, ma'am, got.
Now what happened? Your OMe as a nucleophile can be acted from any of the side, from this side or from this side. What would it be at? OMe with a negative charge. Now if it is act from here, what happened? What happened if it will be act from here? Your negative charge would be go on to the oxygen. You will get the structure in this way, right? This is your triangle, which has been formed by the shifting of hydrogen bond. By shifting of the oxygen, it become shifting of the electron in between carbon and oxygen, it become O minus, and this OMe is been attached over here. We know that a three-membered ring is highly strained. It has very much strain in between, and that need to be opened easily. And for the opening of that, what happened? This negative charge has been utilized to form a oxygen and carbon double bond, and this three-membered ring would be suddenly open, and it will be form a negative charge over here. Correct? When the negative charge would be form over here, you will get the five-membered ring, right? Negative charge come over here, right? Yes or no? And the another carbon, and like as it opened, so this carbon has the another thing like C double bond O and OMe on it, correct? And if you add a H plus over here, you will get what? Five-membered ring. Okay, this H plus would become and attached to that negative charge, and you will get here double bond O, OMe. If you see your products in that, it matches with your this C double bond O, OMe, correct? Isn't it? Yes?
Yes,
sir.
ma'am.
This structure is nothing but what? Your five-membered ring attached with C double bond O, OMe. CO2Me is nothing but C double bond O, OMe. So your second option has been correct. This rearrangement is called as Favorsky rearrangement. Which rearrangement? Favorsky rearrangement. Please write down the name for this name reaction. Favorsky rearrangement. And this Favorsky rearrangement is a ring contraction rearrangement. Means if you have a six-membered ring, you will get the product with five-membered ring. If you have a seven-membered ring, you will get the product with six-membered ring. So in this case, ring has been get contracted. Okay.
Okay, ma'am.
Yeah. Understood? Any query about it? If it's so, let me know. If you not understand any of the step, please let me know. Done? Reactions, they are asking again and again. Shall I ask you one more question?
Yes, ma'am.
know something, because this is the first time I'm taking your question answers, and this application based question you have to solve as many as possible. So question is quite lengthy. Write down it. A hydrocarbon used as a refrigerant. Hydrocarbon used as a refrigerant. Aerosol propellant. It's prepared using Goods reaction. Prepared using Goods reaction. With bromoethane. And sodium metal. In dry ether. The final product is the options are ethane, second is N-propane, third is N-butane, fourth is ethane. They have give you what? Hydrocarbon used as a refrigerant, aerosol propellant, prepare using root reaction with bromoethane. So what is the reactant given to you? That is the bromoethane, correct? Yes or no? Right, and the reaction would be happen with the sodium metal in dry ether. So what is the roots reaction that you should aware first? What is the general reaction for the root? Roots generally, how you're going to write the roots reaction?
A carbo,
Alkyl halide treated with
yeah,
sodium, right? Na, isn't it? You will get what? It will be 2 moles of alkyl halide treated with 2 moles of sodium metal. You will get what?
ma'am, is it the third one, N-butane?
R and R. Yes? Yes, correct. And here you will get what? 2NaX. So this Na and this X would be form the compound NaX, and your product would be coupling would happen in between your alkyl group, isn't it? So your alkyl group is nothing but what? Ethane. And what happened when two ethane would be connect with each other? CH3, CH2, CH2, CH3. It will give you what? Butane. Answer would be N-butane. Clear? Understood or not? Hello,
Yes,
Aditi,
ma'am.
Chandana. What happened exactly in this? This is a general reaction. I'll let you know the answer with your question. Fine. With refer to your question. What happened exactly in this case? See. Mechanism is there in front of you. So here you're going to take two ethane molecule, CH3, 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 CH2, X, any. Bromine they have given bromoethane, right? I'll take bromo only then. I won't create any sort of confusion. When it is reacted with a metal, 2 moles of sodium metal, you will get what here? Plus 2 NaBr, right? And these two would be coupled with each other. CH3, CH2, CH2, CH3. What it is? N-butane. Correct? Yes. So these kind of question would be asked in your JEE examination. Understood?
Yes, ma'am.
Fine. Shall I must like erase it now? I hope both of you have noted it.
Ma'am, 1 minute.
Yeah, I'm done.
Just give me a minute. I'll get back to the content. So basically, we have learned about the SN1 and SN2 reaction, and you have to keep the basic differences between them. Like what is the exact difference in between SN1 and SN2? Once you understand it, you can like differentiate it in well manner, and you can identify which mechanism that particular substrate would follow. Fine. Apart from that, we are going to see the two more reactions. Give me a minute. Now, next concept which we have to learn, that is about chirality. What do you mean by the chiral carbon? Can you tell me? Suppose this is a carbon, okay? If it has a 4 different group attached, suppose here it will be A on the plane of paper, B below the plane of paper, C above the plane of paper or towards you, and here D, which is again on the plane of paper. So such a carbon molecule which attached to the 4 different group is a chiral in nature, which is called as what? Chiral in nature. And we can say that molecule has a chirality. Understood? Yes or no? What do you mean by the chiral carbon? Chiral carbon is a carbon which attached to 4 different groups. Understood? Yes?
Yes, ma'am.
Fine. So, what about this chirality? Why we have to see the chirality and why it is very, very important. Okay. So chirality is important to understand the configuration. Understand what? Configuration of the molecule, whether it is rectus or sinister. Rectus has been shown with a symbol R, capital R, and sinister has been shown by the symbol S. Now rectus means clockwise and sinister means anti-clockwise. Rotation. Okay. Here also rotation. These things you need to keep it in your mind. Examples are given for the chiral. One is given that 2-butanol. 2-butanol. 2-butane or butane to all. Butane to all. What would be the structure for butane to all if I have right? What I'll get normally? CH3, CH2, CH2, CH3. This is your N-butane, right? At the second position, there should be what? OH group should be present, isn't it? Yes, as per the name. I'll get here OH, isn't it? If this carbon I would check, what I'll get? This carbon has been attached to your CH3. One side it will be attached to CH3. Other side it will be attached to OH, right? At one more side it will be attached to hydrogen. And here it will be attached to what? C2H5 or CH2CH3, correct? Yeah, isn't it? So what you come to know, this carbon atom is attached to 4 different groups. 1, 2, 3, and 4. These all 4 groups are what? Different from each other. And hence, this carbon atom is chiral in nature. How it is? Chiral in nature. So the carbon atom which is attached to the 4 different group is called as what? Chiral carbon atom. Understood? Yes?
Yes, ma'am.
Fine. Now, there are certain molecules are given in your textbook. You should identify whether they are chiral or not chiral. Can you do that? Now understand the basic concept about the chirality.
Yes, ma'am.
Fine.
Yes,
Shall
ma'am.
I give you diagram?
Ma'am, could you repeat the last point once again?
Which one? For the chirality.
Yes, ma'am.
Fine. So chirality is a property of a carbon compound in which a carbon should be attached to 4 different groups. If it is attached to 4 different groups, then that carbon is said to be chiral. And if it is said to be chiral, means it is stereoactive, we can say. It can show the stereochemistry. Understand? It can show the rectus and sinister rotations. Understand? So
Yes.
rectus clockwise rotation, sinister means anti-clockwise rotation. Okay, and that is depending upon the priority order of your substituent present onto that carbon, chiral carbon. Okay, so first of all, you should identify chiral carbon. Chiral carbon means what? A carbon atom which is attached to 4 different groups. For example, generally I have shown you this carbon attached to A, B, C, D, 4 different groups, correct? And for example, I have gave you the example for butane 2-ol. If we have if we draw this structure, you will get CH3, CH2, CH, CH3, and at the second position, your OH group has been present. Now, if you see this carbon, second carbon, it is attached to CH3. This is your first group. Second group would be OH. Third group would be this CH3, CH2, means ethyl group. And fourth group is nothing but this hydrogen. So that only I have written in this manner. So what you come to know, this second carbon is attached to 1, 2, 3, 4 different group, and hence it is chiral in nature. Now I'm going to give you a few examples. You have to identify whether it is chiral or not. Understood? Clear?
Yes, ma'am.
Fine. Shall I erase it? Now, first one would be the hydrogen over here. CH3 group. Br and OH. Tell me the carbon at this center. Sometime it would be shown, sometime it won't be shown. Okay, you have to assume there is a carbon. Every corner suggests presence of carbon. Keep it in your mind. Fine. First one. Then second I'll write. Find out which one is chiral among these two. identify among these, then I'll give you this another example. Are you able to find it? Come on.
Mama is still sharing the screen.
Yeah, you are not able to see it.
No, ma'am. Mama, I'll just join from a different device.
Oh, wait a minute. Then I'll stop and again share, okay? Are you able to see now? Able to see the screen or not, Chandana?
Yes, ma'am.
Aditi?
Yes, ma'am.
Are you able to see the screen? Fine. Now check the first one. So this is a carbon, okay, at the center, right? I'll use the different colors. You'll understand it better. Okay. And the C, this is a carbon at the center. This is a first group present on your carbon. This is second group, third group, and fourth group. I'm not given a priorities at all. I'm not showing the Rector Sinister configuration right now. I'm just showing a 4 different group present on the carbon. And as 4 different group is present on the carbon, it is a chiral carbon, and chiral carbon is shown by the star. Okay. Now, if you see the another one, this is a carbon. Okay, it is attached to your first group, second group, and third group. But then third group and fourth group is identical. This is also third group. As the two group identical, there are no 4 different group, and hence it is non-chiral. Correct? Now, if you see this carbon atom, okay, it is attached to your first hydrogen, second OH molecule, third CH3 group, and fourth is nothing but this CH2, CH2, CH3. So this is your fourth group. So 4 different group is attached to this, and hence it is chiral. Okay. But then if you see this carbon atom, first different group, second different group, but then if you see this is attached to CH2, CH3, this is also attached to CH2, CH3. So these two groups are identical and there are no 4 different groups and hence non-chiral. Understood? Now if you check on this carbon, you may see this is a CH3 group. This is what your PR group. Here is CH2, CH3 group. And the lastly here, hydrogen. So 4 different group and hence it is chiral. But then if you see this carbon, it is your first different group. This is your second group, different group, but then it is attached to 2 different hydrogen, right? H2 is written. And as two hydrogens are present, similar group, hence it is non-chiral. Got it? Yes or no? So all 4 groups should be different. Then only we can call that carbon as a chiral carbon. Clear?
Yes, ma'am.
Shall I erase it?
Ma'am, 1 minute. Yes, ma'am, done.
Now we are going to learn about the one or two more examples, and then I'll explain you about enantiomers, stereoisomers. Okay, shall I erase it? Now check it. Here one or two more examples are given. Just identify the chiral examples. Chiral carbon among them. Okay, no, that's a solution only, which I already gave you. No need. Fine. Now we are going to learn about what? Inversion already we have learned into your SN2 mechanism, right? Yes or no? Yes? Now stereoisomers means what? The stereoisomers are related to each other as a non-superimposable mirror images are called enantiomers of each other. Okay. I think I have to share the PDF of the chapter with you to explain you these things. Shall I? Shall I do that? Because non-superimposable images you won't understand unless and until I will explain you. Correct? Shall I do that? Yes or no? Aditi, Chandana, are you there with me?
Yes, ma'am.
Your presentation is not visible.
Not visible. No, I haven't shown yet, but then I'm asking you, shall I show it? Just give me a while. I'll show you and then explain.
Okay, ma'am.
I need to open up your chapter to explain that superimposable and non-superimposable images. Because that part is quite important. So already we have learned, right? Um, Here it is given. This I actually wanted to explain you. Are you able to see the screen now? Hello. Girls,
Yes, ma'am.
Yes, ma'am.
screen is visible.
Yeah, ma'am, it's visible.
Now check here what they have explained you over here, because this is quite important. It's very important, and because of that only I have shared the PDF with you. Otherwise, I don't like to use this textual content unnecessarily. Right? Then this point is very important, and in future it will be very helpful for you. Check it. What they have said in this stereochemical aspect of nucleophilic substitution reaction. We have already learned stereochemistry of the SN1 and SN2 reaction. In SN2 reaction, we have said there is an inversion of configuration, and in SN1, we have said there is a formation of racemic mixture, right? So these concepts are completely new for you. You don't know about the stereochemical aspects. You don't know about the enantiomers. You don't know mirror images and superimposable images, right? Optical activity, chirality, these points are completely new for you, right? You might have not learned it in your grade 11. Have you learned it? Have you learned it? Hello. Because I'm asking you something. Revert me, at least say.
That
Yeah.
Can you repeat again?
Yes, this stereochemical aspect like optical activity, chirality, retention,
Learned that last year.
optimization, these terms you have learned in your grade 11th.
Yes, ma'am.
You have learned. Fine, very good. If you have learned, that's fine. But then a stereochemical aspect regarding SN1 and SN2 that we have to focus in this concept, this topic, that is nothing but optical activity, chirality, retention, inversion, and racemization. So about inversion already I have explained you. Even the racemization also I have explained you, right? But then optical activity, chirality, and retention that need to be explained, right? So in that optical activity, what they are given, plane polarized light produced by the passing ordinary light through the Nichols prism is rotated when it is passed through the solution of certain compound, right? Such a compounds are optically active compounds, and the angle by which the plane polarized light is rotated is measured by an instrument called as polarimeter. If the compound rotates the plane of polarized light in a right or in a clockwise direction, it is called dextrorotatory. In Greek, of right rotating. In Greek, right rotating means what? Dextrorotatory. And it is denoted by D and indicated by placing a positive sign before the degree of rotation. If the light is rotated towards left, means to the anti-clockwise direction, then the compound is said to be leo-rotatory, or the L form of the L form and the negative sign is placed before the degree of rotation. Such a positive and negative isomers of a compound are called optical isomers, and the phenomenon is termed as optical isomerism, right? What they said, plane polarized light produced by passing ordinary light through Nichols prism is rotated when it is passes through the certain compound. If it will be rotated with a certain angle, then we can say that compound is optically active, right? By whatever angle it would be rotated, if it is rotated at the right hand side, it is shown by the positive sign. If it is rotated at the left hand side, it is shown by the negative sign. Okay. If it is rotated with the right hand side, that is called as dextrorotatory or D compound. And if it is rotated to the left hand side, it is leo-rotatory and it is shown by, it is called as a L compound. Fine. Clear about it? So this is all about optical isomerism, and this phenomenon is called as or termed as optical isomerism. Rotation of plane polarized light by the compound. When ordinary light is passing through the Nichols prism and then it has been passed to the compound, it's rotate the plane polarized light, PPL. Okay, that is what? That is what? Optical activity. Okay. Now the next term which you have to learn thoroughly, that is nothing but the molecular symmetry. And it is very, very important with respect to your optical activity. Fine. If the compound has a certain symmetry, those compounds will not be optical active. Please keep it in your mind. Here, asymmetry is essential for make the compound optical active. See what is given to you in the next paragraph. Molecular asymmetry, chirality, and enantiomers we have to learn. The observation of Louis Pasteur in 1848 that the crystals of certain compounds exist in the form of mirror images laid the foundation of modern stereochemistry. They demonstrated that aqueous solution of both type of crystals showed optical rotation equal in magnitude for solution of equal concentration, but opposite in direction. Equal rotation with opposite direction. He believed that this difference in the optical activity was associated with three-dimensional arrangements of atom in the molecule. Now, three-dimensional arrangements of atom is called as what? Configuration, right? Three-dimensional arrangements of atom around the central atom is called as configuration of that molecule. Fine. What has been explained to you about it? See, two types of crystals, right? What is given to you regarding it? Two type of crystals, Dutch scientist J. van Hoff and the French scientist C. Le Bel in the same year 1870 independently argued that spatial arrangement of four groups around the central carbon is tetrahedral, right? And if all the substituents attached to that carbon are different, then the major image of the molecule is not superimposable. Sorry, mirror image. I'm sorry, it's not a major image. Mirror image of the molecule is not a superimposed or overlap on the molecule. Such a carbon are called as asymmetric carbon or stereo center. Apart from that, one more, that is chiral carbon atom. Understanding? If a carbon atom is attached to four different groups, if we take the mirror image of it, if it is not superimposed or overlap on that same image, okay, such a carbon is called as asymmetric carbon or a stereo center, and another name is what? That carbon is chiral carbon atom. Correct? Yes or no? Fine. The resulting molecule would lack in symmetry and the referred to as a asymmetric molecule. Asymmetry of a molecule along with non-superimposably mirror images is responsible for the optical activity in such an organic compound. Means such a chiral carbon atom only optically active. Otherwise, they won't be optically active. Symmetrical carbon will not be optically active. Asymmetric carbon atom which attached to four different groups, only chiral in nature, asymmetric or a stereo center, and that only can give you an optical active compound. Clear? Fine? Yes? No?
Yes.
Girls?
Yes, ma'am.
Fine. This point is really very important, and especially for that reason, I have opened your text. Otherwise, I really not want to open your text. Now, what is about the superimposed and non-superimposed image, right? That we have to see with this pictures. You can see chirality, it's written over here. Able to see? Yeah, an object that cannot be superimposed on its mirror image is called chiral, right? So these are the chiral object. If you keep one hand on the another hand, is it matches completely? Don't join your hand. If in opposite way, if you join palm to palm, definitely it will match. But then if you take your one hand and kept it onto the another hand, only the middle finger would be matched, but then rest all fingers will not be matched at all, right? Or will it match?
No, ma'am, it won't.
It won't match, right? So these are what? Non-superimposable mirror images of your hands. Even same for your feet, right? So these objects are chiral object and non-superimposable mirror images, right? But then if you see the glass, a ball, if you keep a mirror in between, they are superimposable mirror images, right? They can matches on each other clearly. When they matches with each other clearly, they form non-superimposable mirror images, and such images are non-chiral. How they are? How they are? Non-chiral, isn't it? They are non-chiral, and those are non-superimposable, does not match on each other, their mirror images, then they are chiral in nature. And it's all about chirality. Fine. Now, what they have said about this, see, the above test of molecular chirality can be applied to organic molecules by constructing models and its mirror images, or by drawing three-dimensional structures and attempting to superimpose them in our minds. There are other aids, however, that can be assist us in recognizing chiral molecule. One such aid is the presence of a single asymmetric carbon atom. Let us consider two simple molecules, propane to ol and butane to ol, and their mirror images, which is given you in your text. because stereochemistry is not too easy, girls. Stereochemistry require very fine understanding. Then only you can like write the answer of questions regarding that stereochemistry. In the masters, one complete paper is there on the stereochemistry. If any one of you have a future plan to learn chemistry in detail, you'll understand it. But then I won't feel like that any one of you, because we are planning for the JEE, right? Isn't it?
Yeah.
Yeah. So see here they have given the propane to all structure. This is a mirror image for the propane to all, right? You can see this is a carbon, central carbon, which has a OH group with it, hydrogen, CS3, and here it is CS3. Propane to all, and this would be the mirror image of the propane to all, right? Are they superimposed on each other? A and B. B is a mirror image of A. B is rotated by 180 and C is obtained. C is superimposable on A. Rotated the mirror image. Here mirror image, and that mirror image has been rotated. You will get the C. And C and your A are superimposed with each other, correct? But then A and B are non-superimposable. As you can see clearly, propane to all A does not contain an asymmetric carbon. Does it have? No, because you can see this CH3 group and this CH3 group, both are similar group present onto this carbon. So it is not a asymmetric carbon, it's a symmetric carbon, isn't it? All four groups should be different, then only we can call this asymmetric. We rotate the mirror image of B for the molecule by 180 degree, you will get a C, and C would be superimposed with the A, and hence propane to all is an achiral molecule. It's not a chiral molecule. Understanding? It does not attach to four different groups, and hence it is achiral. Clear? Yes or no? Already we have solved the questions regarding this. Yes or no? Bacha, are you there?
No, ma'am.
Yes, ma'am.
You have to revert me. Whatever I'm explaining, that is quite important. For that reason, I'm showing you this. Otherwise, I would not. Now see the next. This is butane to all. It's a mirror image. You can see all four different groups are present on it, right? And when you rotate, you will get this, right? But then this rotated image F and D will not be superimposed with each other, right? So those were superimposed with each other, and hence those were achiral. But then here non-superimposable, and hence it is chiral. You can check 2-butane all, right? This is a mirror image. When you rotate this, what happened? OH would go here, C2H5 would be up, CS3 would be down, and hydrogen would be as it is at its place, isn't it? So this F and D will not be superimposed on each other if you keep. It's just like our hand structure, as I told you, right? Yes or no? If you keep one hand on to the another, only your hydrogen would get matched, but then both other groups will not be matched on each other. And hence, butane to all has a 4 different group attached to the tetrahedral carbon, as expected is in chiral. So some common examples they have given, right? And what they said, if the mirror image has been superimposed and if they are not superimposed on each other. The stereoisomers related to each other as a non-superimposable mirror images are called enantiomers. So A and B in a figure 6.5 and D and E in the figure 6.6 are enantiomers. Right? Yes or no? The stereoisomers related to each other as non-superimposable mirror images. These are what? Non-superimposable mirror images. Right? And hence they are enantiomers of each other. An enantiomer possesses identical physical properties like melting point, boiling point, refractive index, etc. They only differ with respect to rotation of plane polarized light. One would be rotate at right hand side, another would be rotate at left hand side. So one would be dextrorotatory and another would be leo rotatory. These things you need to keep it in your mind about the enantiomers. Clear? Yes?
Yes, ma'am.
Fine. Now, about the mixture, chiral mixture, they are going to explain you in your textbook. Then I don't want to say focus much about rest all things. I'll just explain you about racemic mixture and the racemization. Now, enantiomers may be dextrorotatory and the leorotatory. It can be shown by either small d sign or by the small l sign. If these plus minus enantiomers are present in one bowl, right, in the form of mixture, so that mixture is called as the racemic mixture. Understanding that mixture is called as what? Racemic mixture. See, a mixture containing two enantiomers. Here they have said a mixture containing two enantiomers in equal proportions. Equal proportion means 50% of D and 50% of L. Right, in equal proportion. That time we can say it has a zero optical rotation, because when plane polarized light would be passed by this mixture, it does not get rotated, because the rotation caused by the dextrorotatory compound would be cancelled by the leorotatory compounds present into the same mixture, and hence effectively there would be no rotation, or we can say zero rotation, and hence as the rotation due to one isomer will be cancelled by the rotation due to another isomer, such a mixture is known as a racemic mixture or racemic modification. A racemic mixture is represented by DL or plus minus sign before the name, right? For example, plus minus butane to ol means it has both the enantiomers of butane to ol, right? Dextrorotatory as well as leorotatory. And the process of conversion of enantiomers into racemic mixture is known as racemization. When enantiomers are converted into racemic mixture, this process is called as what? Racemization. Now clear the terms about your stereochemistry. Yes, optical activity, asymmetric carbon, symmetric carbon, then chirality, enantiomers, stereocenters, retention, and racemization. I hope all these things you have understand in clear manner. Inversion retention is vice versa. Huh? Keep it in your mind. Here it's given retention. Retention means what? The whatever product would be formed, that has the same configuration as of your substrate or the reactant. We suppose your reactant has a stereochemistry or retention in sorry, what we can say, R compound asymmetric carbon has a dextrorotatory rotation. Your product also have a dextrorotatory rotation in the plane polarized right. So that is called as the retention in configuration. Inversion means configuration is being changed, and retention means configuration would be remain same. Okay, these are the basic terms. See, retention of configuration is the preservation of the spatial arrangement of bonds to an asymmetric center during the chemical reaction or transformation. And hence, retention, in a retention, whatever your rotation of plane polarized light, that would be maintained in the product as well. In a general, during reaction, no bond or the stereo center is broken. It will be remain as it is. Clear? And it happened whenever your SN1 and SN2, your like what we can say, leaving sorry, nucleophile, when it attacked from the same side of leaving group, that time only retention of configuration would be obtained. These things you need to keep it in your mind. Okay. If attack of the nucleophile from backside, that time it would be inversion, right? From both sides, that time it would be racemic mixture. Okay. And when it attacked from the same side of the living group, then it would be retention. Okay, these things you have to keep it in your mind. Backside attack, racemic mixture, both side attack, and retention, same side attack at the living group. That time you will get retention. Clear? Any doubt in this? Then let me know. Clear, girls?
Yes. Got it.
Okay. So this part was quite important and hence I have to be little slow. Quarter to 1, I guess I gave you time till 12:30, but then I have extended it for the 15 minutes. I hope you don't mind. Clear?
Yes, ma'am.
Fine. So regarding this stereochemistry, I'll give you a few examples in the next class. And if possible, I'll take you evening as well. I'll text you regarding. Okay. And
Okay.
we'll take the electrochemistry as well. Fine. Simultaneously. I'll have a word with Manisha ma'am related. Clear? And whatever questions you will get about this chapter from JEE NEET question papers, try to solve. If you can, if you can't, then please post it. I'll help you regarding. Clear?
Yeah, ma'am. Got it.
Fine.
Yes, ma'am.
Shall I erase it? Let's say close it. I'll end the meeting. Take care. We'll meet it again.
Thank you, ma'am.